Okay, so I'm taking a step back. I'm taking a step back because I have the feeling in the last videos I've just been rushing too much towards getting the solution from a code perspective. And I'm kind of realizing I don't yet fully understand the blocks. This might actually help me. I did have a couple of voice conversations with the Grok AI assistant yesterday, and to be honest, like I feel pity that I couldn't record them because they were actually very, very helpful. Why? Because I think you could stay more or less high level. I'm gonna try to see if I can. I think I'm not so sure if I. No, I think we can leave it in auto, and I just want to have. I want to try to break down that concept a bit more because it's gonna help me. I think it's gonna help me understand how to build the code. Otherwise, it's kind of just really like a black box. Everything else I understand now. And but the blocks concept still I don't really get. So I don't. Okay, let's walk through an example. Let's do an example, so I can try to understand what blocks of a group algebra KG are from an intuitive level first. Please stay brief and short in your replies. Use a simple field, integers mod 3 maybe. Use a simple group, C2. And let's construct step by step the group algebra. Sorry. Sorry. Let's construct the group algebra. Field K, group G, KG. Like, let's go slow. So what I want to know is I want to know things I want to know. How do you combine the elements of K and G? Because what I solidified in that conversation was basically a few things, right? So we know that a group algebra is a vector space. We know that, I think it kind of helped me understand intuitively as well. So the insight that if in an algebra you have, in a field you have two operations, product and addition. The operation of a group in that context can be interpreted more as composition, I think, right? I think. So how do you combine the elements? I'm trying to kind of self-reflect a bit as well, because what I liked about that conversation is that what I'm speaking out loud, I was getting feedback on, right? Here I'm just talking about, like, I'm talking out loud, but then I have to type my questions. And so what I'm talking about is not really necessarily being evaluated, which this is, I have to figure out a way to change these. I think, because I'm thinking, yeah, but that's for another moment. Okay, let's not get distracted, because I'm thinking about like extending a bit the Omega Quest interface so that I can actually use it to help me guide through the problem solving flow. So how do you combine the elements of K and G? how do you interpret the operation of G in an object that has already like addition and product. Let's see. So field in group G, those are definitions. Step to construct a vector space. So Kg is a vector space over K with basis G element. Exactly. So this also helped me understand. This is also something that I understood from the conversation, that the elements of G are used as bases for this algebra. So the elements are the formal sums alpha E plus beta G, where alpha and beta belong to K. Alpha, beta. And if you have two of these elements, they sum. Okay. Yeah, well, you're essentially, so the coefficient sum, and then this thing extends kind of. And scalar multiplication, they just distribute. So it's just, so they just, this lambda just distributes in alpha E and beta G, and that's it. But I fail to understand how okay, it's always two elements. Okay, so it's always, I think this is maybe one parallel that this, one easy way that I can, one easy way that, because this not confuse this notation was confusing me a bit, but now I'm thinking, do you know how in with complex numbers you also have this notation, right? So you always have like A plus BI, and I'm thinking that's kind of, it's the same, right? Because here you're gonna have the identity in a way, right? In a way, I think so, because the basis vectors, yeah, I think so, because then you have, you know, of course you can have just A, which just means that the component of the imaginary component is 0, right? And the complex numbers are a two-dimensional vector space, right? So here you have the imaginary parts, but you can still have your real numbers here, right? So those numbers here, they all have B equals 0. And I now it just occurred to me that I think that notation makes sense, because you can still, it's two dimensions. You can still, you could still represent them like these, right? As kind of vectors or something. But that's also okay, I guess. Okay. Okay, that's something at least. Add a ring structure multiplication. Extend group multiplication distributively over addition. So this is, okay, these times these plus these times these. It's like the way that you would just apply the distribution law. Okay. So it ends up being like these times these these times these plus these times these, and this is E, and then the cross product, and yeah, okay. So let's get multiplication. That's all good. Then we have combining elements of K and G. K provides coefficients. Combos. Not so sure what it means, like vectors, but with group multiplication added. Interpreting G's operation in KG. KG already has vector addition and multiplication by K. G's group operation embeds as ring multiplication. What? Intuitively, G acts on KG by G acts on KG by left multiplication. Turning KG into a module. So G times an element of KG turning KG into a G module. Isn't it just that G defines how the G operation just defines how these elements are behaving, E and G, right? They just define. That's a little weird still. But okay. I think it just defines, like it just used to solve what things like G times G mean. Because that breaks a bit my concept that this is, or like what I said before, that this addition multiplication and kind of like a I don't know what to call it. It's not stretching, it's not extension, it's not it's composition, I was saying, but it's also not composition really. No, that's not what it is. Anyway, this convolves groups action with vector structure. Useful for representations, decomposing modules into blocks later. How do we... Can you now give me the definition of a block of KG? Let's try to break it down with this example in mind. But this now, okay, this helps, this kind of, what would it be? What would the group be here? Well, yes, the group is the following, right? So the group is basically such that you have elements E and I squared is basically -1. We know that. Because like I is like a rotation in that direction. So I squared is -1. So then it's minus I, and then it's so is this C4 then? Let me ask Grok. What? That was Gork. Yeah, sorry, Gork.com. So if you remember the page, quick question: are the can the imaginary numbers be built as group algebra of C4 of the reals? C4 is, okay, no, C4. Yeah, okay, maybe. What is it talking about? Yes, okay, that's all I needed to know. Complex numbers C can be built as subalgebra, okay, of the algebra RC4. Okay. Blocks, let's go through these, okay. So a block of a group algebra is a minimal two-sided ideal indecomposable in the direct sum decomposition of Kg as a ring. It's too much at once here. Correspond to a primitive central idempotent in the center of Kg. Each block is associated with an irreducible representation of G over K and forms a direct sum in Kg's decomposition. Okay. Breaking down with his example. The Kg structure, we know. Center of Kg is the elements of Kg such that xy equals yx for all y in Kg. So the center is the whole group algebra. We need idempotents that are central and primitive. Equations mod 3. So we have non-trivial idempotents E, 2E plus G, 2E plus 2G. Okay, Y. And we seek idempotents that are orthogonal. I'm not ready to go too much into detail. Pieces of Kg tied to irreducible representations. But what are these representations? Let's take a step back. What does it mean to decompose Kg? Stay high level, please. What are we decomposing? What are we decomposing around or against? Smaller pieces called blocks. we decompose KG around the center of the algebra. Okay, so think of KG as a machine combining G's group actions with K's linear structure. Decomposing KG is like sorting the machine's functions into independent modules, blocks, each driven by a core switch that isolates a specific representation of G. Trivial and sign. I don't. Okay, I. This is where I'm getting. This is where I get lost. So G in this case is C2. So how does this generate blocks in KG? Because it's something related to G being applied to K. Linearly, okay. Decomposing KG into blocks means splitting into two-sided ideals. What are two-sided ideals? I can't seem to break through this sentence. Two-sided ideals, each tied to an irreducible representation of C2 over K. Okay, so KG is like is these. Multiplication does these. Irreducible representations of C2. C2 has two iReps. Whatever that is. E maps to 1, G maps to 1. Irreducible representations of C2. I don't understand that part. Why are you mapping these to 1? Let's focus on... Why are we mapping G elements to 1? In the translation G, we map both group elements E and G to the scalar 1 in K. This means C2 acts trivially on a one-dimensional K vector space, where every group element acts as the identity transformation. That's what that's what I was missing. A representation of G over K is a homomorphism invertible linear maps on V. Acts as do nothing. Okay. The trivial representation is the simplest way G can act on a vector space. I'm onto something here. I have to stop now. But I'm onto something here. I think I've kind of broken through. Okay, so it's about the different ways that G can act. And for some reason that's then these homomorphisms. The second one was sign. How do you interpret this one? G minus 1, which equals 2 mod 3. This preserves C structure. Let's go back to the original sentence here. I've called blocks. Each block corresponds, let's ignore this in the middle here. Each block corresponds to an irreducible representation of the group G over the field K. I think that's an important thing. What is a representation of a group G over a field K? It's a homomorphism. Assigns each G to an invertible linear map. So it is mapping elements from G to the field. Why is this useful or used to define group algebra blocks? I don't understand why. Why would you map these? You see, that's constantly too much text. I find myself not reading these, and I don't really need to read these. Representations of group J over field K are used to redefine blocks of the group algebra because they provide a way to break down KG's structure into minimal indecomposable pieces that correspond to G's irreducible actions on K vector spaces. KG is a ring combining G's group operation with K's in structure. Representations describe how G acts linearly on vector spaces. Decomposing KG is semi-simple. KG decomposes the direct sum of blocks. Blocks break KG into smaller algebras, each corresponding to making it easier to study. Symmetries. Do nothing versus flip signs. Sure, but I know that it's not the case that it's because C2 has order 2. I'm gonna get there, okay? I'm gonna get there. So I'm not 100% sure why we're doing Why do you need to? Why do you need to do these? I need to think about these. Why do you need to? Yeah, I have to go. But I'll do another session as soon as I can. Bye bye.